Hi, welcome to the Signal Path. In this episode, we're going to do another product review. We'll be taking a look at the Siglent SNA5000 series network analyzers. Now, Siglent has been making some impressive strides into the RF domain. I've reviewed their vector signal generators up to 6 GHz. They have spectrum analyzers that go up to 7.5 GHz or so, and they're going to push even higher than that in frequency. So they're going to put some serious competition against some of the bigger players. And I'm interested to see this particular model because this is a 4-channel 8.5 GHz network analyzer with TDR and spectrum analyzer options in the firmware. It has a fantastic form factor and honestly it works really well. We're going to have to try and see some of its limitations, some of the places they can improve the firmware, but overall this is an impressive instrument for the bench, especially in the price performance ratio, which is one of the things Siglent essentially excels at. So let's go ahead and dig deep into this. I really want to do a lot of experiments. We're going to take it apart and see how it works on the inside, look at the architecture and see what it can do. And here's the instrument up close. This is the SNA5000A model from Siglent. This is a 4-channel, 8.5 GHz network analyzer, and the starting frequency is 9 kHz, which is competitive with other units on the market. Now, if you look at the design of this, I think it's really nice. They've done a great job making it clean, and I'll show you the depth of this thing is tiny. So for form factor, it's really quite excellent. The 4 ports are all in the front with activity lights at each port, of course, and they're all type N, which is common for this type of frequency range. The damage level is 27 dBm, half a watt, which again is a little bit better than actually the Keysight E5071C, which is a 26 dBm damage level. And damage level at these instruments is quite important because you may be measuring active components and active amplifiers, and you want to have as much protection as possible. We do have a soft power in the front. We do have 4 USB ports, and that's because this thing has native keyboard and mouse support, so you may be plugging a lot of things into it. And they do a really good job with the GUI, especially for remote access. We'll talk about that in a second as well. Now, the LCD screen is 12.1 inches, 1280 by 800, multi-touch of course, and I hope that other manufacturers are taking note. It is possible to make a non-reflective LCD screen for an instrument that's not a mirror essentially. So they have a matte finish on it, which is great. I wish everybody did that. In terms of the button layout, this is what you expect to get from something like a network analyzer. The only recommendation I would have is that I wish they had moved this enter from here in the middle of the arrow keys and they had replaced this enter key with a mode key, because this instrument supports multiple modes of operation and switching between them now is in the menus, as we will see. But I think that some improvements of that is going to come. So let's take a look at the back of this unit. And here's the back of the instrument, and just like the front, it does have a clean, flat design. The handlebar at the very top tucks into the instrument when it's folded down, and we do have 4 BNC connections in the back. These are the built-in bias Ts of the instrument at full frequency range the front, so you can bias any of the ports independently as you would expect. We also have a 10 MHz input-output, trigger input-output, and they're all also independent BNCs, which is great because sometimes you don't want to have the same port used for both functions, as you may need to rewire everything if it's sitting in some setup. So I'm happy that they kept that independent. It runs pretty quietly because it has a fairly large fan, which is also great. It does have an OCXO option, and this one does have that. And you may ask, well, why does a network analyzer need an OCXO? That's because this thing is also a spectrum analyzer, and you would need the frequency accuracy that comes with that. Not to mention that you can take advantage of the OCXO with a 10 MHz output and synchronize other instruments taking advantage of the OCXO of built-in into this one. So we really thought about that as well. You have an earthing ground in the back, which is a nice touch. So you can have, like a strap around your wrist connected to it, LAN, USB, and an HDMI port output, which is fantastic. So you can connect it to a larger screen if you want to. And of course, we have the power input. If you look at this, you can see how narrow it is. It is absolutely amazing. So for a 4-port network analyzer, I think this is one of the most compact ones I've actually seen recently. So I'm really happy about the effort that they put into this. Now, making network analyzers compact typically comes at the cost of dynamic range, but this thing still boasts a very good dynamic range, and that's one of the very first things we're going to try out and to play around with. And then we're going to get into more and more of the advanced functions. I do also want to talk about the architecture of this and do a little bit of a teardown, because the architecture lends itself to a lot of future firmware upgrades and new capabilities that can come from this. So we're going to take a look at that too. So the instrument with the back off, and you can see it is fully shielded. This is a common practice where the outer shell of the instrument is just basically for cosmetics. The real EM shielding and structural integrity is achieved with these cages. So let's take that a step further. So the instrument is pretty cleverly put together. Essentially, there are 2 parallel cages, and the digital stuff here in the back, right, is part of the digital interfaces, as well as the bias Ts, the power supply, and the fan are sandwiched in between. There's another cage, and underneath it are all the RF components, which themselves are going to be inside of their own little modules. Interesting design on the bias T here. So we have the 4 bias T connections going in, and then we have the cages. They're alternating, one at the top and one at the bottom, top and then the other one is at the bottom, and they seem to be hand soldered. Now normally what you would want is you would want them to be both at the top and the bottom, so cages everywhere. But I think they put it a little bit too close and they probably couldn't hand solder this anymore, and that's probably why they've alternated it. Ultimately you'd have to reflow it anyway. That's an interesting thing. Now on the other side of this board there are actually fuses. Here, these are the 4 fuses for the biased inputs. That's a little bit inconvenient because if you damage the fuse you would have to open the instrument to replace it, which is quite a bit of a hassle. You have to remove a whole bunch of screws, but you can get there. Normally those fuses should be accessible from the connector itself, but I guess it's better that they are there so you could replace them. Nothing unusual about the power supply. The 10 MHz reference comes over here. Here's the OCXO goes into the board. But yeah, all the actual RF part is underneath. And the fan is here is primarily for the RF parts because I don't think the power supply generates a lot of heat. It's probably fairly efficient. They have a custom board up here which interfaces with the power supply, and then this entire cable bundle goes into the unit a layer down. I'm going to see if I can easily remove this because I think it should just come off and then we should be able to see what's underneath it too. Alright, and here's the main part of the instrument, and now we can appreciate the compactness of this unit and how much stuff is going on. So just like we expected, we have 2 of these boards. You can see they're exactly on top of each other, each of them responsible for 2 of the channels of the network analyzer. So 2 channel network analyzer here, 2 at the bottom, connected from these connectors in the front to the 4 connectors in the front panel. That makes the 2 channels. We have the synthesizer over here, and you can see that each of the synthesizer outputs goes into one of the 2 channels, and that's responsible for the down conversion and doing the frequency translation required for the network analyzer as well as the spectrum analyzer option. Then we have on the right side over here all of the various IFs from these boards. You can see all the channels coming through here. We have 4 and 4/8, which makes sense. You need 8 digitized channels for a network analyzer that has 4 channels, and they all go in there, and that's probably how they get digitized. Somewhere on this board is the ADC. Now there's also a big computer interface board. This is common, so this entire thing can be used in many different instruments. Siglent has been doing that also for quite some time, and the rest of the interfaces is just simply for synthesizers and so on. You have a whole bunch of power supply which used to be plugged over here. It's pretty thin. Remember, underneath all of this is still the LCD screen, the panel, the buttons and everything. So they really spend a lot of time making sure all of these things fit together, which is pretty impressive. And here's how everything else is connected, and you can see all the biased connections also coming from there, and the 10 MHz in and out, and the reference for the OCXO. Yeah, very nice. I have to say it's quite impressive how far they've come. This is completely custom design from the ground up. Not an easy job. So here's the RF board out of the enclosure for one of the 2-port network analyzers. There are 2 of these of this instrument. And there's a lot going on here, both on the front and on the back. And I think this warrants a closer look so we can really analyze and understand how this is put together. So let's go ahead and take a look at this board a little more closely. So I've taken 2 photographs. This is the top of the board, the business end of it, where all the RF components are, and here's the other side of the board, and I've flipped the image so that the connectors are all lined up the same way. There's still some important stuff on the back as well, which we will talk about. So let's look at the front and see what we can observe right away. Now first of all, this has an axis of symmetry. You can see that the stuff here on the left and the stuff here on the right look very similar. That is to be expected. This is a 2-port network analyzer, and there has to be a axis of symmetry somewhere in the middle of this, because port 1 and port 2 are identical in operation from a network analyzer point of view. So here's port 1 here, and here's port 2 on the other side. There are also 3 other connectors you can see on the right and left. Again, they're symmetric, and 3 connectors here on the top left, which we will talk about. That very first thing this thing needs is obviously a path for it to apply the stimulus to the device under test. So the signal has to go this way. It also goes the other way, but of course that's for the reflected signal. So that signal is going to need a bias T. And if you look closely, you can see some inductors over here, and there's another one over here. These are typically cascaded inductors to achieve the frequency response you're looking for, and capacitors and so on, and that's your bias T. So it looks like that this port and this port are just simply the bias T ports of this. Then we have 2 other ones which we'll have to talk about. So right off the bat, you can see that here we have a resistive coupler. The signal can flow in this direction, but there's also a couple of signals that can flow in this direction. In reality, these signals are all flowing at the same time, but you can use the mathematics to calculate which is what. And that's a lot of other things you can talk about. In this point, I've covered it in different videos, so I won't go into the details. Now here, suffice to say that these resistive couplers obviously have a disadvantage because they have lower dynamic range, and the EM-based couplers have directivity, and they're obviously much better, but they're much larger, much more bulky, much more expensive, and this is common technique to reduce the cost of network analyzers. So we have two couplers, and again you can see that they are identical on the left and the right side. These resistors are the coupling parts. So these two paths all need to be simultaneously stimulated and digitized and all that. We'll talk about this. So let's see where this stimulus signal of these ports actually come from. So we can trace this back. If I go ahead and trace it back this way, okay, you can see that it comes this way, and then we have this symmetry here and here, so signal flows in both of these directions, and then it reaches over here in the middle, and it reaches over here in the middle where you have a switch. Now there's also attenuators and switches in the way, multiple of them. It's interesting to see that they have switches along the way that terminate into 50 ohms, probably for additional isolation. So this point in here means that you can only apply the stimulus to one port at a time, but that's normal. That's how network analyzers are supposed to do. So depending on whether this path is active or this path is active, you get this stimulate on port 1 or port 2. Now remember, these paths are from 9 kilohertz to 8 gigahertz, so we have to cover that entire frequency range. But more importantly, it needs to do that with various filtering, so that it doesn't have a lot of harmonics, which can cause problems, especially in the spectrum analyzer mode. So we can continue this. Now we have a shared path. There's actually two paths here. You can see the signal can go this way or it can go straight, and this gives you some gain through this amplifier here. You can adjust amplitudes and so on. This is just to control the power of the whole thing. That's normal. Again, we go over here. This is a programmable attenuator, and we continue this way. We have two more programmable attenuators, and then we come over here. Now you can see there's two paths. The signal can go this way, or the signal can go this way. This component up here is a doubler, and doublers are required because you typically do not have a VCO that covers the entire range. So if you want to hit 8 gigahertz or 6 gigahertz, you're going to need to double the signal at some point. So they join back again here. So depending on how it sweeps, some part of it will be chosen this path, some part of it will choose this path, and there are filters all around these doublers to get rid of the harmonics. Now if you go back this way again, you can see we have another dual path selection, and that in fact is yet another doubler in the path. So they're probably doing two doublers in a row, or maybe there's some part of it they're doing one doubler, another part a different one. It all depends on how they're managing the harmonics. It doesn't really matter, because ultimately it's just a matter of doing the frequency translation to get to the 8 gigahertz signal. And then we come over here and we can see that again we have two separate paths. We have this path, which itself splits into multiple paths. These are filters, they're discrete filters. You can see all the different filters, but all these paths ultimately actually join up. You can see they all split here, but then they all come together and they join here. So just treat this entire path as basically one path with multiple subsections for different frequency ranges once again. And this path over here hits this component. Now this component is a mixer, a downconvert mixer in this case, where they're using the IF of this mixer, I believe, to cover everything below 1.5 gigahertz. And we'll talk about why that would be needed. Now the other path would be this path, which is taken directly. If you look at this, the LO of this particular mixer, this is an LO signal coming in, the LO of it comes from another synthesizer board. And again, they're using that to go below 1.5 gigahertz. Now in the other path, at the core of it, right over here, we have a synthesizer IC. This is a fractional end synthesizer. It needs a VCO. Here's this VCO. This VCO works from 2 to 4 gigahertz. So if you look here, there's a little coupler over here. This coupler is used to couple a signal into this PLL chip, and that's how they close the loop around this VCO. So this is essentially your entire synthesizer, and I think the reference for that synthesizer is coming from here. So that generates a signal. This signal comes over here. It either goes this way directly, or it goes up, goes into the RF of this one, uses this one for down conversion, and then it goes this way. And then they join all together here anyway. So this is essentially to cover anything from 9 kilohertz to 8 gigahertz. So let's review that one more time, just in case it was confusing. We have a VCO from 2 to 4 gigahertz. I can use a multiplier to bring that all the way to 8 gigahertz. And I can use this mixer over here with an external LO coming in to cover frequencies below 2 gigahertz. So they don't have a divider, they have a mixer to cover that. So the synthesizer needs to generate this LO, and it needs to generate the reference signal in order to do all of the stimulus generation. So that covers basically the signal that hits the device under test. That's what covers the signals going out of this way and out of this way. So that's great. That's our stimulus path. And this path here, again, is symmetric to this one on the other side that I just covered. So you don't, actually, sorry, that's not the part. This path here is symmetric to the other one. So what about this part over here? Now this part over here is what they're using to generate the IF of the network analyzer, and that's how they basically measure the reference and the reflected signals, the two channels that are required to measure the S parameters. And if you look carefully, you can see that one path comes from the coupler and the other path is coupled to the incident wave, right? So these are the two, this way, and there's some amplification and path selections, and then they go into this area. Now there's a chip here that's not populated and a chip here that's not populated, and I believe those are down convert mixers. And you can see there's exact symmetry on this side. All right, there's two more here, and then this chip is also missing, this chip is also missing. But both of these ICs are going to require an LO. That LO is independent of the LO generated or the RF generated by this entire section. It's going to need a different signal for the down conversion to create the necessary IF, and that comes from here. This is the other synthesizer part of the instrument, and that's what makes this architecture a little bit flexible, because you can use this to create a spectrum analyzer, and you can use this part to create a synthesizer, so you can have all of that. So it's a lot of power built into the hardware, which is nice. Now how does that work? We're going to flip the page to the other side. That's this connector. You can see this connector over here, it splits, it goes all the way across the board. Ooh, I don't like this trace. And it ends up here, and on the other side it comes over here and goes in there, right? So that signal is identical on both sides. If I flip it, it'll end up exactly here, and that I believe is the LO that feeds these chips. Now what happens to the IF? Well, the IF seems to come out, and it appears to be differential. It goes through a balun here and a balun here. It converts it to single-ended, and I think those single-ended lines basically end up in these two connectors. So that becomes your two IFs for the two parameters you need to generate the S parameters for this board. And again, there's a perfect axis of symmetry on this side, and that makes the other two. And that's it. That's the entire architecture of this board. So there's a lot of stuff going on, but most of it is just switching between different filter paths and different attenuation settings and different multiplier settings. It's really not that complicated, aside from the fact that this must have taken a tremendous amount of time, of course, to do the frequency planning for, but it's not overly complex. A lot of these other chips, like these ones, all of these ones, they're just inverters. They're used to drive all of these absolute crazy number of switches. But if every component on here is almost exclusively from analog devices and from Hittite, from the old Hittite guys. So that makes sense. They're all quality components. And there's I think this is a CPLD. I didn't really look at it. It could be an FPGA. There's a connection here to control this, of course, from the rest of the instrument. And there's a bunch of high sensitivity or very low noise voltage regulators, which is also what you need to drive a synthesizer, and a VCO, of course. And that's about it. I don't really see anything else here. We're talking about most of these filters. I didn't do an x-ray of this board because it really wasn't necessary, but a lot of these filters are built with discrete components, which you can get away with up to about 8 gigahertz or so. So that's it. That is the entire configuration of this. And just to note why there are two doublers, I think there are two doublers because it needs to cover 8.5 gigahertz. And if you multiply this by 2, it only gets you to 8 gigahertz. So there's a half gigahertz missing. And I think this architecture probably can do more. So maybe there are other versions of this that they're thinking about, even to higher frequencies. So maybe that's why they chose that architecture. I'm not sure. But they're definitely using some pretty quality components on here. And they have taken care of a lot of things. These long lines are probably shielded very well. Otherwise, this would never work. You would not get a dynamic range. And yeah, that's how you also get a network analyzer out of this, a spectrum analyzer out of this. So I think that's about it. So now that we covered all of this, let's go ahead and play with the unit. So let's go ahead and use the instrument for some experiments. Now we're going to explore the GUI as well as the capabilities of the unit along with the experiments themselves. The very first thing to do to get a network analysis is to do a calibration. Now the instrument supports a variety of passive as well as electronic calibration units, and once you connect this to the USB, it automatically detects it, and it has a list of supported ones that of course you can work with. So first thing first, let's go ahead and calibrate channel 1 and channel 2 using this ecal, and then I have something to measure to push the dynamic range of the instrument and compares how it behaves on various channels. Now in order to make the recording a little bit easier, I'm going to use a remote server to connect to this. You can use a web browser, type in the IP address, or you can use VNC, and that's what I'm going to do. It's connected via Ethernet to a wireless router over there. I'm just going to connect over Wi-Fi. Just keep in mind that the refresh rate of the VNC screen is going to be a little bit worse than what I see in real life here on the instrument. But remote access to this is probably something a lot of people are going to do, so it's going to be a good test as well. So here's the GUI of the instrument. This is in full screen, of course, and we have all the required things on the screen that I think helps perform the measurements. Right now we're looking at S11. This is trace number 1. At the bottom we have a general status of all the different settings of the instrument. and you can add traces and channels and different measurements and cursors and so on right there from the top. And we can bring the menu here also on the right side, so you can see different menus, for example, to select things like frequency, stimulus, and we're going to take a look at that. Now, first thing first is you can access a couple of them down here. Since I'm going to do a very high dynamic range measurement, first thing is to change the IF bandwidth. We can make the IF bandwidth quite a bit lower. Let's go to something like 500 hertz. By the way, there's an undo and a redo here at the top. That's also quite nice. If you change something or you're not sure what you changed, you can always go back. Now, the frequency is from 100 kilohertz to 8.5 gigahertz. That's full span. That's fine. Now, I'm going to increase the number of points here. Instead of 201, let's go to, let's say, 500. Okay, so it steps up every 17 megahertz, and you can see the sweep happening, which is reasonable for a bandwidth of 500 hertz on the IF. So it's pretty much okay. The only other thing we want to do is we want to change the amount of power, because again, we want to push this to its highest dynamic range, and we're measuring a passive device as the first thing we're going to measure, so we don't care about the power in terms of linearity. So we're going to change the power here, and the highest we can do for this in terms of stimulus is 10 dBm. Okay, so we're going to enter that. And the power is connected on all of the ports, and we can see that the coupling is on, in which case we're only using port 1 and port 2 anyway, so it all lines up quite nicely. Now we can also change the calibration. We can go to calibration over here. We have a lot of options. Now this is pretty significant. So we have port extension, which is crucial if you want to move the reference plane of the ports to somewhere else. It also has fixture and adaptive removal, which is a manipulation of the different S parameters. So you can have measured things and you can remove them. It can be quite handy if you want to change your DUT or you want to bring the measurement plane closer and eliminate things like fixtures and adapters. It's quite nice. This is a fairly advanced function, but nowadays everybody basically includes it. Let's go under ecal here. So we already have an ecal already plugged in there. So it's loading the data. So we're going to do a 2-port calibration like this, and it's an SOLT. And we want to actually, before I do that, let me change the orientation to manual just so that we can see what that looks like. And connected that again. So that's fine. We're going to do an SOLT on 2 ports. Next. So I have actually port 1 connected to port B here and port 2 connected to port A. So I have it reversed on mine, but it doesn't really matter. We go OK on there, and we're going to do a measurement. So you can see it's going through the various measurements. It's going to have to do the open, short, load, and through. That's the SOLT calibration procedure, and it should be done. There it is. It is done. Now if I finish, it's going to apply the calibration. So there it is. You can see it says that the correction on 2-port is applied. So now I can go ahead and remove the actual ecal and put the device I want to measure. And here's what we're going to measure first. So this is a multi-stage cavity filter, and it has an extremely high quality factor. So it has a very, very good rejection out of band. It's 15 stages. It's already been adjusted. You can see all the different screws have been meticulously adjusted to bring all of the different poles and zeros in the same locations to get the response we're looking for. So this allows us to really push the dynamic range, because we want to see what is the floor of this, what is the maximum amount of rejection we have in the pass band versus the reject band. So it's all connected up again to the same 2 ports we were using. Let's go and take a look at its response. So here we are looking at S11, which is interesting. You can kind of tell where the bandpass would be now. But what is interesting more for us is the S21, because we want to see the rejection here. Now you can measure the S parameters, you can change the trace type, or you can add multiple traces, as we will see. But the instrument also gives you balanced response, and we'll do a separate experiment for that. But also there is a receiver and the wave measurements too. So you get the raw data of the A and the B parameters on all the channels in any configuration that you want. This is pretty powerful if you want to write your own code, or if you want to do something interesting by taking advantage of having essentially the low-level data available. It's pretty handy that this is there. I think you can do some pretty cool things with it. There's also the spectrum analyzer option, which we will take a look at later on. So let's go ahead and change this to our S21, which is what we want to see. There you go. Now we need to move this curve a little bit to a more favorable location so we can actually see what we're dealing with. So if I go on to the amplitude or scale here, let's go ahead and change the reference level. We can put the reference level at, let's say, -50. There we go. And you can see we still don't see the floor. So we're already looking at about 100 dB of dynamic range here, and this is obviously can be better than that. So we're going to have to change the scale to maybe 15 dB. There you go. There it is. That looks a little bit better. So we can maybe move the reference from 5 to 4 here. Oops, that's the wrong way. Always goes the wrong way the first time. There it is. There we go. So we can already see that we have some floor here. Now we want to analyze this floor a little bit better than what we were doing. Even though we're looking at the bandwidth of 500, we can always average, because you can see every trace is a little bit different. So we're at the very, very close to the noise floor of the instrument, and we want to change that. So we can go on averaging here. If I change that to average and bandwidth here, let's go ahead and turn the averaging on, and we can set the average to something like 32. And you can see the IF bandwidth is also right there, okay? So it's going to count the averaging here individually. So this is you can see the noise continuously goes down. That's to be expected. Let's give it a second until the averaging is done. So the averaging is complete now, and we see the filter response a little bit better. I put a marker over here. You can, of course, move this marker left and right, but I'm interested in seeing where the peak is. So we can use the search function and do a peak, and do a peak search, and there it is. So we're at 3.6 gigahertz with an insertion loss of about 1 dB, which is pretty good considering how much rejection this filter has and how many stages it has. We can also automatically calculate the bandwidth of this filter in the search function, and there's the bandwidth. We can turn the bandwidth on, and you can see that this bandwidth is about 210 megahertz, and the standard frequency is correctly reported. You also get the loss and the quality factor. Now there's also a sound on fail here, and this is because you can turn this on, set some specification, and if you're measuring multiple parts, if one of them doesn't meet the specification, the instrument will warn you, which is also quite handy. And you can also do some tracking. So if this filter is moving left and right and you want to track and constantly report the bandwidth, the standard frequency, and the quality factor, this can be automatically happening in the background. All of this is great, and these software features are pretty important. Let's go ahead and take this a little bit. So if you're looking at 1 dB of loss, 125 dB down, that would represent 125 dB of actual measured dynamic range. And 125 line would be somewhere over here. So for most of this, the instrument has no issue meeting that 125 dB of dynamic range. Now there's two unusual blips here. One is around this frequency. You can see, there it is. It's trying to measure the filter bandwidth around that area. And that is at frequency about 2.8 gigahertz. And if I bring it all the way over here, there is another one here at frequency of 7.7 gigahertz. So are they real or are they not real? Well, these are already pretty down. If you look at the amplitude of this, we're sitting at minus 100. And if I look at the amplitude of this, we're sitting at minus 112. So we want to know, is this part of the filter response? Because if it is, the filter needs to be adjusted. Now this is a very tough measurement for this instrument, because if you remember, port 1 and port 2 share an RF port. You have to get 125 dB of isolation between port 1 and port 2 in order to be able to measure that whether this peak is real or not. So instead, I'm going to change the setup just to double check to see what's going on. I'm going to use port 1 and port 3. I'm going to do exactly the same thing, same calibration, same everything, but instead we're going to use those two ports. So instead of measuring S21, we're going to measure S31. And those two ports do not share an RF port. And let's see if we can get a bit more dynamic range from the instrument and find out if these peaks are real or are they the artifact of the instrument itself. All right, here we are. Instrument is calibrated. Now we're measuring between port 1 and port 3. And here we are. Now we're measuring S31. Everything is exactly the same and the averaging is complete. And take a look at that. That blip that used to be here, now we're sitting at minus 128 dB. So that artifact was not from the filter. It was actually from the instrument itself. And as I said, it's because it's so hard to get isolation within the same board better than 125 dB or so. Now the other blip over here, that one is real, and that's because that's a multiple of the standard frequency, and these other modes can kick in with these kind of filters. This is a normal problem for these filters. So we now are fairly confident that this is actually something that's related to our own design, and we could try to address it and so on. So yeah, so if you want to get the highest amount of dynamic range from this instrument in a two-port measurement, you should always use either the odd or the even number ports. Now you can't do this if you want to make a four-port measurement, of course, but that's another reason why it's so important to understand the architecture of any instrument so you can get the most out of it. Now for most parts, the 125 dB of dynamic range is met no matter which ports you use, but it gives you even better if you use the odd or even number ones for two-port measurements. So next we're going to take a look at an active device. Now measuring active devices with S parameters in linear mode, there are some precautions we have to take, which we're going to talk about. But this is also an active amplifier splitter, meaning that you can apply a differential signal into its input and it will split and amplify it into two outputs. So that's why it has 6 ports on it. This is supposed to work up to 28 gigabit per second, so it should be a fairly broadband block. Now at the same time, this thing can do single-ended to differential conversion. We'll have to take a look at that. We also want to see how matched these ports are. There's almost unlimited number of things you can measure with something like this in order to truly understand it. So what I've done is initially just connected 2 of its inputs and 2 of its outputs for 1 of its ports into the 4 ports of the network analyzer. So this should allow us to essentially fully characterize it. Let's go and take a look at what we get. So I went ahead and I did a 4-port calibration, which is basically the same as a 2-port, except if you have a 4-port ecal, it will do all 4 at the same time. And if you have a 2-port ecal, it will prompt you to change the ports until you get all the terms required. And the 4-port calibration is active. And if you click on that, you can see that all the calculations are done and the correction is enabled. You can also do a receiver power cal, which is pretty helpful if you want to ensure that the amount of power arriving at your DUT is precisely at a certain level, or is fixed across frequency. This is pretty useful. I'm glad to see that it is part of the firmware as well. Now there's another thing I have to make sure. Because I'm using an active device, I want to make sure it operates in a linear operation, and in order to do that I have to reduce the input power to below a certain value. There's some disadvantage to doing that. So I'm using a minus 30 dBm input power, and you can see that if I go under frequency and I go under power, I can set it to minus 30 dBm. Now I can go as low as minus 50, which is pretty nice, because when you use the instrument as a synthesizer, which is one of the capabilities it has, then you can go from minus 50 to plus 10. So you also have a nice synthesizer dynamic range, as well as the fact that you can do the same thing for S parameters. Now at minus 30 dBm, it is also harder to do the calibration, and I didn't do a very good job on the calibration in this. It doesn't really matter for our purposes, just for demonstration. You can see that when the S11 is really good, in this case, we're not getting a very clean response, and that's because, again, the incident power is so much smaller. But it doesn't matter. When the device has a lot of gain, this is not an issue. So it is all set up and nice, but we still are only measuring S parameters on all the 4 ports. So if I go measurement here, and I go to other, you can see that I have a 16-point matrix here that allows me to make all the different combination of S parameter measurements. But really what I want to do is I want to make a differential S parameter measurement, because this is a differential input, differential output amplifier. Well, we can do this by going under balanced menu. Under the balanced menu, we can change the topology of our DUT. So the simplest topology would be just a 2-port where you want to have a differential stimulus. So what this will mean is that it's going to use port 1 and port 2 of the unit, and it's going to call it a logical port 1. And it will tell you what the differential and common mode response of this port is. But that's not really what we want. We actually have a complete amplifier, so we want balanced. So in this case, I've used port 1 and port 2 at the input of the device under test, and port 3 and 4 at the output. And that creates 2 logical ports, 1 and 2, and that's going to give me a 4-point in the matrix of the S parameters, but now I get all the combinations of common mode and differential measurements, which is exactly what I want to look at. Now you have to be careful. This, even though is a differential S parameter, it's not true differential stimulus, meaning that the signal is applied here, and then applied here, and then from that mathematically computed what the differential response would be. That is okay if the device is linear and time invariant, but it would not be if the device was operating in a nonlinear mode. Some network analyzers allow you to do a differential stimulus simultaneously. So a signal would appear here, and one would appear here at the same time with 180 degrees out of phase or with 0 degrees in phase for calculating and measuring common mode and differential responses. In that situation, if the device under test response is different between common mode and differential, you will catch that. But here, we cannot do this with this instrument. Although, given the fact that there are 2 independent synthesizers, if they do have control over the phase, they could, in theory, provide that feature, which is a fairly advanced feature for network analyzers. Not everybody uses that feature. So anyway, so here's our device under test configuration. So when I do this, I will have a logical port 1 and a logical port 2. So let's go ahead and say, okay, now, if I go over balanced measurement, you can see that I have a collection, a 4x4 collection of all the different kinds of stimulus this device can have. So let's measure the differential S11. And what does that tell us? It tells us that the input of this amplifier differentially is very well matched to 50 ohms, below minus 20 almost for the entire range. Now this stops only at 8.5 gigahertz. You can also see that at the very beginning we have a big drop, and the input is not matched near DC. That's because this amplifier is AC coupled at the input. So that also verifies that that is indeed correct. But this is fine, but really what we want is the gain of the amplifier. So what do? Well, we go under the measurement. We want to look at STD21. In this case, the amplifier has gain. And I can put a marker down on this. If I put a marker, you can see that it has 22 dB of gain and is essentially, constant in gain across the entire frequency. Even at 8.5 gigahertz, we still have the same gain. That's because this is a 28 gigabit per second amplifier. So this still continues flat for quite some time. But of course, we're at the limit of the network analyzer. Now we can also go and look at the isolation differentially. You can see it's very good. It goes below -50. So basically, it's reverse isolation is excellent. We can see other things. For example, we can see what happens when you apply a differential signal at the input and you're looking for the common mode signal at the output. And that, if you look at that, that's pretty good. It tells you that this amplifier is very good at rejecting anything that's in common mode at this output. So the signal at the output is going to be fairly well 180 degrees out of phase, which is exactly what you want. Then you can go ahead and do all of these different measurements, or you can just simply plot this, which would be the equivalent of the common mode rejection of this. Now it is better than 50 because it's above there, so we have to go over here and check the scale. For example, there you go. So you can see it has a fairly high common rejection. Now this is going to be not the cleanest measurement again because the stimulus was very low, but this is to be expected. It has a very good common mode rejection. So yeah, so this kind of stimulus is available in this instrument, and it's a powerful combination. Now what I do want to measure is actually a particular balance configuration which will be interesting in this amplifier. So if I go over topology here, we do also have single-ended to balanced, of course. This will measure how well an amplifier can have a single-ended input and convert to differential. There's also one called single-ended balanced. So in this situation, because this is a splitter, an active splitter, I want to connect a differential input and then use one of the ports to look at one of the outputs and use the other port to look at the other output of the other side and then terminate the remaining. And this tells me how well matched those two outputs are going to be. So let me show you what that looks like in the setup. And here's our configuration. So we are going to do a differential stimulus measurement on this port, and then this amplifier is going to split it on the right side and on the left side. You can see the two other outputs are terminated. So we have a differential output here and a differential output here. And now we can compare the response this way and the response that way, because this amplifier is doing that using, of course, integrated circuit technique. So it's using a splitter amplifier internally. So the matching of that in terms of phase and amplitude can now be analyzed. So using this topology now, we can go ahead and measure the response to each individual output of this amplifier splitter device that we have. So what I'm measuring right now, let's actually go over here. I'm looking at a response from channel 3 to channel 2. So I'm looking at the differential channel 3 stimulus to the single-ended channel 2 output, and that's going to give us one of the outputs of this splitter. And the other one is going to be the exact same situation, but now we're going to be looking at port 1. So the output, so from port 3 to port 2 and from port 3 to port 1. These are, remember, the logical ports, and those represent these three ports here, port 3, 1, and 2. Has nothing to do with the actual ports of the instrument anymore. So let's go and see what that looks like. And here it is, and you can see we have a flat gain again. We already measured this, we expect this, except the gain is lower because we are only looking at one of the outputs of the differential amp and the other side is terminated, so we're going to get less gain. But I'm interested in seeing how well these two output amplifiers actually match together. So we're going to add another trace over here. So here's the trace. Now we're going to change this trace to show us the other output that we are interested in, which is this one. Okay, so now they're on top of each other. So both of these traces now have exactly the same scale at the same time. You can see they're very well matched together. Now let's go ahead and change the scale a little bit more. Maybe we can even change this to 1 dB per division so we can really exaggerate the differences between them. Yeah, they do deviate a little bit with respect to each other. But what about the phase of them? Because these two outputs should be exactly in phase, and that's what you expect them to be, and you want them to be in phase because this amplifier is supposed to essentially do nothing other than split the signal perfectly and amplify it, of course. So we're going to add another window here. In this window, I'm going to now, instead of plotting the actual response in magnitude, I'm going to plot its phase. And there we are. If you take a look, you can see that the phases are very well matched. This is an unwrapped phase of exactly the two signals that we see at the very top. And then, yeah, they're essentially on top of each other. So it does a very good job at splitting those two with respect to each other. I don't know why it changed the scale on this one, because I didn't ask it to change that. Maybe it was a little bit of a bug there. So there you go. So even though we have a tiny amplitude drift between the two outputs, we actually have a very nice phase match between the two of them. So you can continue doing more and more. And of course, in terms of formats, this thing supports a variety of displayed formats that you can look at the S parameters and analyze them. And there's a couple of other little things that I wanted to show you without going into too much detail. And the math functions are also quite nice. And we'll take a look at those math functions separately when we do the TDR experiments, because it's quite powerful. But in the math functions itself, you can add equations, you can convert them, and the conversions are nice. So if you don't want to look at S parameters, you can look at Z, Y, or other types of parameters, even 1 over S, which is helpful in some control system that you can take a look. Yeah, so they really have thought about this. They put a lot of effort, and there's also time gating in here as well. But once we do some of the other capabilities, we'll get into some more of these details. So let's use the instrument to make some nonlinear measurements. So here I have a little amplifier, and this amplifier is connected on port 1 at its input. There's a 10 dB attenuator at the output, and that is then connected to port 2 of the network analyzer. This now allows us to characterize this, not just its S parameter, but also its large signal behavior, because we have some unique sweep features in this instrument that we can use for that purpose. Let's take a look. So let's take advantage of the different sweep types the instrument offers here. So we've been using linear frequency sweep, which is the common one everybody uses. There's also logarithmic frequency, useful for some filters. CW time just gives you a tone as a function of time. So if you have some dynamic behavior of the circuit, you're looking for matching as a function of switches or biasing or something that changes as a function of time, you can use that. And then there's a segment sweep, which only sweeps within different segments of the frequency range that you can predefine. There's a segment table up here. That's useful because if you have a very low IF bandwidth, or if you want to do a lot of averaging and there are some frequency ranges you're not interested in, you just don't sweep those because it will take a long time. This way you can speed up your measurements, especially in automation, significantly. And there's also power sweep. Power sweep does exactly what the name suggests. It sweeps the power of the stimulus at a certain fixed frequency so that you can see what happens to the circuit across that power. Very useful for catching nonlinear behaviors. Even though the instrument doesn't tell you actually what those measurements are, you have to interpret it yourself. This can be put into the firmware. But I wish it would also do IP3 or IM3, because I think it can do that in some situations because it has two sources. But I have to take a close look at the architecture to be 100% sure. But nonetheless, here's the power sweep. So if you look at the power sweep, I have set the CW to 2.4 gigahertz, and we're starting at minus 30 dBm, and we're stopping at 0 dBm. So it's a fairly wide range of power sweep. When the input power is very small, very low, we expect the signal to be, the circuit to be very linear. And if I look right now, the amplifier is plugged in, but it's not turned on. And the input matching is pretty bad. It's about minus 2.7 for S11 when the input power is low, and it's actually it's constant essentially across all the input power. This tells us that this amplifier has an active input matching circuitry, that it relies on the biasing of the circuit and the active behavior of the input transistors to be matched to 50 ohms. So if I turn it on, I would expect to match to get quite a bit better at low input powers. There we go, it's plugged in. And as expected, you can see that the input matching gets quite a bit better. Now with a minus 28 dBm input, we're at minus 18 dB S11. But because it is an active matching, we also expect it to degrade once the amplifier begins to compress at the input. And as the input power increases, you can see at some point that the return loss gets worse. So at 0 dBm, the return loss is now minus 10. It's not terrible, but it's certainly not where it used to be. Now this doesn't help us so much because sometimes you want to see how it moves across the Smith chart. You want to understand how the impedance changes, both in phase and magnitude, and not just its magnitude. So in that case, we're going to go over here under format, and we're going to change that format to Smith here. And then you can see exactly how it looks like. Now, unfortunately, I can't move this with the mouse when it's in Smith chart mode. You're going to have to go into format. You're going to have to go into the marker and change the power there yourself. So when the input power is about minus 24 dBm, you can see that we are, minus, about 64 ohms or so. So we're reasonably real in impedance, minus 1 ohms as well, and close to 50 ohms. It's not perfect, but it's close. But once I go to 0, which is the end of the sweep, you can see we are now at 85 ohms and 22 ohm in the imaginary side. So we got pulled into higher impedances and into a more inductive behavior at the input, which is not good. But that's what happens to circuits when they are matched, and they can have different properties. So let's go ahead and add a window to this. So on the bottom window, I'm now going to plot S21 instead. So we're going to go over here, we're going to go under measurement, we're going to plot S21. Now it's a little bit more interesting for us because I can bring this marker back over here, and there is an attenuator at the output of the circuit. Let's not forget that, and that attenuator is 10 dB. So when the input power is low, the gain of this circuit is about 30-31 dB, which is good. That's what you would want. This is supposed to be a low noise amplifier. At some point, this is going to drop by 1 dB, and that's the input and the output compression point of that amplifier. You can measure exactly what that is. Let me see if I can set up a difference marker here. And here's our delta marker here. So the reference of the delta is at minus 30 dBm at the input. The gain is 20.8. There's a 10 dB attenuation. That makes it 30. And we're going to adjust this until we're 1 dB down. Oh, that was close. Right there. There it is. 1 dB down. So we had to move 11 dB away. So from minus 30 to about 11. Okay, so we're putting around minus 19 dBm into it. So the input compression of this amplifier is minus input 1 dB compression is minus 19 dBm. And we know that it has about 30 dB of gain. So it's putting out roughly 10 dBm at the output 1 dB compression. So you can see how quickly you can measure this because you have the power sweep available to you. Power sweep has other advantages and use cases as well. You can even do power sweep during linear frequency to compensate for the losses of cables. And remember, I mentioned that you do have the ability to do receiver power cal too, so you can even level that at the device. So the instrument also allows us to use the built-in synthesizers in CW mode and essentially use the entire instrument as a multi-channel synthesizer. So I have it here connected to the Keysight MXA. Let's take a look at the quality of these tones. So the instrument actually allows you to apply CW to any of its 4 ports, and it's combined with the spectrum analyzer feature, which is a different story. We'll talk about that later. So right now I'm generating a 1 GHz tone at 0 dBm, and you can see it has a very good THD. Every once in a while there's a bit jump. That's because the spectrum analyzer sweep is finishing. They're going to have to adjust that in firmware later on. But it's a pretty nice tone. Now if I go to 10 dBm, you would expect the THD to get worse, but that's not entirely unusual. There you go. You can see that we do get a hit there. But for 0 dBm, it's actually a very clean signal. Certainly one of the best I've seen in this class of instruments in terms of dedicated synthesizer. Let's change the frequency there. Let's go somewhere a little bit higher. Let's say 3 GHz here. Let's see how it looks like at 3 GHz. There it is. You can see it's not too bad. So it generates a fairly nice tone. I think as a synthesizer, since there's 2 of them and you can set them to different frequencies, this is a fantastic feature for an instrument of this class and the cost profile that it has. I think this feature only is available with the spectrum analyzer option. So let's stop here for now, primarily because the TDR option and the spectrum analyzer option deserves a lot of attention on its own. Now I'm working with the Siglent engineers to modify how the firmware for the spectrum analyzer particularly works and how it embeds the synthesizer and some of the other quirks that I saw in there. I think it makes sense to give them a chance to make some improvements before we review the spectrum analyzer and TDR, because then it's more refined and it's also a little bit better because it's going to have the longevity of what it looks like and how it behaves for people who want to watch it. As always, I hope you stuck around to this point, and if you ever do purchase one of these, feel free to let Siglent know that you learned about it here on my channel. I don't get any of the sales or anything. All the links that I provide are directly to the products. They're not even tracked. And this is a combination of review and, of course, educational material free for everyone to see. As always, I'll see you in the comment section.